Dzień dobry Państwu. Welcome everyone on our weekly Thursday colloquium on our institute. Today we have an ordinary, extraordinary colloquium, which actually is to advertise and remember the wonderful paper, Kołos-Wolniewicz paper, and the basic physics behind it. So we do have a pleasure to have three excellent speakers working on the fundamental physics, and this event was organized by our institute, but also by the Polish Physical Society, the Toruniu chapter, which we have the representatives here, and also it was organized by the Aleksandra Jabłońskiego Foundation. So I will now give floor to one of the organizers.
Okay, so hello everybody, welcome in the name of Polish Physical Society, Polish Toruniu chapter. I'm really glad that everybody is interested in variational principle. You know, in physics we have several important principles, and variational maybe is one of the most important ones. And we are sitting in these particular places, I guess because due to variational tendency to have as low potential energy as possible. Otherwise we will be spread it all over this room. So people sitting here, they use this in practice. And of course in quantum world, this variational principle, especially in the non-relativistic quantum mechanics, is terribly important. And 8 years ago, not exactly, because the paper has been published with the date December 15, a paper appeared which has shown that time that apparently calculation shows that variational principle is not necessarily correct. This was a problem that time, a big discussion, and till now we have all papers full of references to Kołos-Wolniewicz paper you see here. It is still active, and the last references are from June 24, which I could encounter. So it is important issue and mentioned in many, many occasions. Today we have three excellent speakers, Professor Karwowski, who cited at least few times this famous paper in his work through quantum chemistry ages, and we have also a recipient of ERC grant, Professor Piotr Wcisło, who will talk about experimental aspects of this discovery and this system, and at the end we will have short accounts about the person of late Professor Wolniewicz. Jacek, the floor is yours, and we will have discussion, short question and answer sessions after each presentation. They are not full-time presentations, shorter ones, but we want to cover many aspects of this very interesting event, and of course related to our city and Warsaw.
Thank you very much. I'm grateful to the organizers for giving me this privilege to participate in this extraordinary event, and for their trust that I still can say something coherent. And I will try to take this challenge. So I will talk about this event. Today we celebrate this, as Professor Nowak said, this very remarkable event, because 60 years ago, Włodzimierz Kołos and Ludosław Wolniewicz demonstrated that quantum mechanics can give, when applied to many body system, four body system in their case, can give results which are very precise, they're more precise than the best experiments of this time. And this opened, in a way, a new chapter in applications of quantum mechanics to many body problems, and in particular of quantum chemistry. And I will try to explain briefly why it is so. So the quest for new physics what is the new physics? It's a term which appeared relatively recently. When Kołos and Wolniewicz worked on their problems in Chicago, this notion didn't exist yet. But the issue is defined here. When we compare results of highly accurate calculations and measurement, we can test validity of the theory. And when these results are sufficiently accurate, then the discrepancy doesn't, this discrepancy do not reflect errors in formulation or, say, unprecision in formulation of the theory, but reveal gaps in our understanding of nature. And that means they can serve as a tool to falsify the theory, to show that theory is not completely correct, that something essential is missing. And this missing part, this part we are not aware of, give kind of window, wormhole to the new, to what is called now new physics. When you remember how theories like, for example, quantum mechanics emerged from studies on the rather very narrow subject on radiation of black body. And let me start with a famous quote by Toshiro Kinoshita, that it is important to keep pushing the limits. New physics might reveal itself in the next decimal place in theory and measurement. This is very important for what I'm going to talk about, that essential thing in finding a gate to new physics is precision. And in order to see how it emerged, let's come back to very, very old times, 1894 in Chicago, that is 30 years before emergence of quantum mechanics. In quarterly calendar of the University of Chicago, Albert Mulliken, Michelson delivered a talk entitled "Some of the Objects and Methods of Physical Science." A sentence from this talk of Michelson is frequently misquoted. Therefore, I put here a rather long section of his presentation, of his talk. He said that very soon the scientific work will demand accuracy 10 to 100 times greater than current standards. An eminent physicist has remarked that the future truths are to be looked for in the 6th decimal place. This misquotation of Michelson is that people usually say that this is him who said that this is future truth is to be looked at the 6th decimal place. And then there is another couple of sentences which are very important for what we are discussing now. It is only in very recent times that it has begun to dawn upon the mind of man that there is another world, the world of molecules and atoms. When will a second Newton appear to solve the riddle of that complex microcosm we call a molecule? Remember, that was the end of the 19th century, 20 or 30 years before formulation of quantum mechanics. And Albert Michelson, maybe it's in place to explain who he is. He was the first American Nobel Prize winner in science. He received this award for his works on measurement of velocity of light with new kind of interferometer he developed. And last but not least, he was born not far away from Toruniu, in a place called Strzelno. This is about 100 kilometers from here. And I encourage everybody interested in history of science to visit the museum of Michelson in Strzelno. And then this riddle mentioned by Michelson has been solved about 40 years later. In mid-20th century, Robert Mulliken and Clemens Rutan created in Chicago, in the same university in which Michelson worked, created laboratory of molecular structure and spectra. And it became a leading center for atomic and molecular studies, leading in the world scale. They managed to gather all scientists, the best scientists of the world, engaged in the applications of modern physics to studies of molecular properties and of applications of modern, at that time, computers started to be used in solving physical problems, and to use numerical methods to this aim. And in 1966, that means very soon, shortly after this laboratory started really working on full scale, Robert Mulliken received the Nobel Prize in chemistry. And the Nobel Committee formulated that he got it for his fundamental work concerning chemical bonds and the electronic structure of molecules by the molecular orbital method. And now we come back to our heroes. One is Włodzimierz Kolos. I refer to them as young scientists. Yes, they were very young as for present standards. Kolos was how long old he was? 40 or 38 when he started to work on this subject. He was a chemist interested in using methods of quantum physics to explain chemical processes. Please note, he was interested in applications of quantum physics to some phenomena to explain chemical processes. He was not so much interested in foundations of quantum physics. He took it for granted that it's correct. He wanted to explain chemistry. He was a graduate student of Leopold Infeld and very quickly earned his doctorate and professorship. For the ones who maybe are not aware who was Leopold Infeld, he was a very famous Polish theoretician who created Center of Theoretical Physics in Warsaw, and he was also very influential in the many scientific centers all over the world. Therefore, he could promote Kolos. He was a very good student, and shortly afterwards he got a long-term fellowship in this laboratory created by Mulliken and Rutan, and joined the group of Professor Rutan. And the second person, Kołos-Wolniewicz, he was a physicist, and he was really not interested in chemistry, and in particular in quantum chemistry. He was interested in quantum field theory and in fundamental theories describing nature. He wanted to work in quantum field theory, but for several reasons it didn't work. And then he joined, he simply attempted. There was no group of Kolos at that time. Kolos got his habilitation more or less at that time, so he could be a supervisor of doctoral thesis. and he became graduate student of Kolos. And for his doctorate, he developed something which didn't exist at all at the time, the non-adiabatic theory of diatomic molecules. That means he solved quantum mechanical problem of 4 particles. And the results of his thesis remain one of the most advanced theories of molecular structure until now. And now, coming back to Chicago, Wolniewicz and Kolos was already in Chicago, and in the late 50s, Rutan started their project on development of computational method in molecular physics. That was something entirely new at this time. Nobody heard about using computational electronic machines to solving mathematical problems, and the computers at that time had smaller capacity than your cell phones today. Nevertheless, that means people involved in using computers were able to solve very advanced, very complicated problems using computational tools. And Kolos was very enthusiastic about these applications, and with his enthusiasm, and Wolniewicz, with his very good expertise in mathematical method, joined this group and were really excellent supplements to them, because that was something new, and that was this mathematical knowledge was brought from different area, from quantum field theory. Wolniewicz brought this new approach he developed in his doctorate. And in this approach, he had extended the variational treatment of Born-Oppenheimer molecule to the non-adiabatic treatment with relativistic and quantum electrodynamic correction included. At that time, nobody knew how to calculate in chemistry quantum electrodynamic effects, and non-adiabatic treatment of molecules was also rather unknown. The nuclei were treated as classical particles, and electrons moved in the field created by this nuclei. The theoretical formulation of Wolniewicz is outlined here. So he treated hydrogen molecule as a 4-particle system rather than 2 particles. So nuclei were also treated as quantum particles. All relativistic and quantum electrodynamics contributions were included in his treatment, and the theory was derived, as Professor Nowak mentioned before, from the variational principle. And consequently, the calculated total energy can never be smaller than the exact one. Total energy is not measurable quantity. One cannot measure it directly. One can transform results of measurements and eventually derive from them total energy. Directly measured is dissociation energy. And this consequence of variational principle, when applied to dissociation energy, means that the dissociation energy can never be larger than the exact one, because total energy comes with the minus sign to the dissociation energy. And now this theoretical formulation of Wolniewicz was published in a joint paper in Reviews of Modern Physics as a joint paper with Kolos, non-adiabatic theory for diatomic molecules and its application to the hydrogen molecule. And as far as I can see here, it's 1963 year. And here another kind of personal features of both Kolos and Wolniewicz. Wolniewicz was a rather shy and withdrawn person. He had several outstanding results in his thesis. And for example, one of them was about using Gegenbauer polynomials to evaluation of some integrals. He published paper on this in Acta Physica Polonica. This paper has probably 2 or 3 citations. Nobody knows about her. Several years after, Sachs, an American physicist, derived the same method and published it, as far as I remember, in a Physical Review or maybe in Journal of Physics A. And this paper has several hundred citations, and it contains, in principle, the same material as a paper of Wolniewicz. So if not Kolos, and Kolos was very sort of good organizer, good manager of science, and probably Wolniewicz wouldn't publish his thesis in Reviews of Modern Physics, but maybe also in Acta Physica Polonica, or maybe in Postępy Fizyki, because he would not consider this to be essential where it is published. But because it was published in Reviews of Modern Physics, it's a very well-known and densely cited paper. And now we come to the core of our discussion. When this method of Wolniewicz was applied to calculation on a hydrogen molecule, the paper was titled Accurate Adiabatic Treatment of the Ground State of the Hydrogen Molecule. They got theoretical dissociation energy of H2 larger than the experimental value. Here is the value they got, and here is the experimental value. And that was adiabatic treatment. They still didn't develop non-adiabatic application, and their expectation of Kolos and Wolniewicz, was that maybe it is due to adiabatic approximation. So immediately Wolniewicz started to trying to find a source for this discrepancy, and 1.5 years later appeared his paper, where Wolniewicz was the only author, Variational Rotational Study of Electronic Ground State of the Hydrogen Molecule. And here he confirmed the previous results, that theoretical dissociation energy of H2 is larger than the experimental value by 3.9 inverse centimeters, and this discrepancy exceeds possible computational inaccuracy. And most important, he was able to prove that this discrepancy is not due to the adiabatic approximation. So it was not clear what was the reason, and after another 1.5 years, Kolos and Wolniewicz got their final result published in PhysRev Letters, and the title is Confirmation of the Discrepancy Between the Theoretical and Experimental Ground State Energies of H2. And here is their final results, that refined calculations using more flexible wave function and non-relativistic four-particle Hamiltonian with corrections for the non-adiabatic effects, relativistic and radiative, still place the theoretical total energy 3.8 inverse centimeters below the experimental value. Well, that was what they got. And now their final conclusion in this paper I displayed on previous transparency. Since this is exact quotation from the paper, since all known effects of non-negligible magnitude have been included in the theoretical calculation, and since we see no reason to doubt the accuracy of the experimental value, the explanation of the discrepancy remains to be found. And only after this paper and this statement, Gerhard Herzberg, who got afterwards Nobel Prize for his work for molecular spectroscopy, corrected his old experiment. The puzzle mentioned before was solved, and I thought it was the master's mistake. In a new experiment, Gerhard Herzberg corrected his result and got value larger than theoretical one by 0.2 inverse centimeters. And here maybe one remark be in place. Herbert in his paper referred to the original results of Kołos and Wolniewicz from 1964. He didn't talk about these more recent corrections, and he tried to somehow present this discrepancy as something rather irrelevant, calling it a small discrepancy, but yes, since they make big fuss out of that, let us correct, and we did correct, and this is the corrected value. And now, if there is no new physics, it was just experimental mistake, then the question comes, what is new if this result? Why we are so excited about this? And the most important is that was important step in the transformation of quantum chemistry from a qualitative rationale of molecular structure to a quantitative theory challenging experimental results. This is very important. Before works of Kołos and Wolniewicz, quantum chemistry was mostly semi-empirical theory explaining why molecules are bound together, why benzene molecule has such and not other properties. And here are points, 3 main points which explain in more detail what is new. Here, for the first time, molecule with more than 1 electron, that means molecule and other molecules than H2 plus, all particles were treated explicitly as quantum objects. For the first time, all QED and relativistic corrections were included. For the first time, computed molecular energy proved to be more accurate than spectroscopic one. So what does it mean, more accurate than spectroscopic? This is a philosophical question, and explaining what does it mean would require another talk, probably. It's not simple to explain. And here is Lutoslav Wolniewicz with a friend in his Toruniu office. Why do I present this picture? I remember this period here in Toruniu, and I remember this thrill of excitement about possibility of finding a wormhole in quantum mechanics. Not in variational principle, because variational principle is a mathematical theorem, and it's always valid. But in formulation of quantum mechanics, because if variational principle is violated, that means that something is wrong in basic formulation of quantum mechanics. And this is Wolniewicz at the time of this event, and at this time I remember when Professor Kołos came from Warsaw, and they discussed that maybe quantum mechanics is incorrect already on the 6th decimal. And here for our young colleagues, I give something I like very much. This is 5 don't rules of Leo Sasaki, who got a Japanese who got Nobel Prize in 1973. And Wolniewicz obeyed all these 5 rules except for one. Don't allow yourself to become overly attached to any one authority in your field. They believed that Herbert cannot make a mistake. And now legacy, pushing the limits. Here you have a table of dissociation energy of H2. This is a result of Kołos and Wolniewicz in 1964. Then Wolniewicz himself, 83, 93, 95. As you see, there is permanent, constant improvement of this energy, permanent growth. Then 21st century comes, Piszczatowski, Komasa, Puchalski, Pachucki, and others, and you see 2019, there's 8, 7, 9, that is significant figures correct, and perfect agreement with experiment between experimental and theoretical error bars. And tribute. 1 year after Wolniewicz died, Wim Uwaks in Amsterdam organized a workshop dedicated to Lutoslav Wolniewicz. And there is a series of conferences inspired by works of Kołos and Wolniewicz, aimed at searching for new physics by use of very precise studies on small molecular systems, and this is where also Piotr Cisło is engaged very much. Here, as you see, this is not a single conference. This is the history of these conferences. So thank you very much for your attention, and I am sorry for talking a little bit too long.
Thank you so much, Jacek. Listening to good talks is never too long, so we enjoy it because this movie is going on. We will have a following plan. We will have few questions now for speakers, and then at the end it will be a general discussion led by Piotr. So any questions, raise your hand and then you will get a mic. Nobody knows. Jacek, do you know what computers did they use that time? Do you have any
well, they use IBM. I don't remember number, but I know that the memory of this computer was 100 was an order of magnitude smaller than the one we have in our cell phones now. So it was, for present standards, it was a very small computer, but for standards of the epoch, it was the biggest computer in the world. I can tell you an anecdote about this big computer. Because of this big computer, this Chicago Center was considered as a sensitive place from military and political point of view. And there were several very suspicious people working in there. One of them was a communist Kołos. Another one was another communist, Wolniewicz, coming from the communist countries. And another one was a militarist coming from Japan, Professor Fusinaga. And another one was a fascist. That was Professor Serafin Fraga, for whom I worked as a postdoc in Edmonton later on. Actually, he escaped Spain to avoid Franco regime. His family escaped. Anyway, they were considered to be suspicious because they were from these suspicious countries. And they worked in this center where also all military projects, that was the biggest computer in the world at that time. And all military projects were run on this computer. So Serafin Fraga told me that when they were going to toilet, then a guard assisted them. They couldn't move freely over this institution because of security reasons.
Right, so sometimes military...
And that was a period, well, more or less, of McCarthy hunt for anti-American activities and things.
Yes, these publications, they got thousands of citations, so they are famous. And I wonder to what extent it was a rational approach or accident that such rumor appeared. What is your opinion?
Whether they were aware that they are looking for new physics. Yes. Well, yes, I can answer this question actually, because I had a chance to talk several times with Wolniewicz about this. He considered his work on small molecules, on the hydrogen molecule, not as a tool to interpret properties of hydrogen molecule, but as a way to challenge quantum mechanics, to check whether it's correct. But the result he got was not obtained in the quest for discrepancy. He just wanted to get as accurate energy as was possible. And both he and Kołos didn't expect, as far as I know, that they can go below the result of experiment. But, well, when it happened, then, of course, they believed that maybe don't believe, they dreamed that maybe they found something which breaks the principles of quantum theory. And therefore, in the title of my presentation, I also use word disappointment. Maybe it's not really disappointment, but in a way.
Yes, so this is interesting example of very good physics, but not necessarily a very good theory, because as far as I know, theoreticians, they usually don't check anything with experiment. So it is strange that they were looking for some data from experiment. I'm kidding a little bit about that. Okay, any questions from the audience? Because we do a nice discussion, but time is running. No questions, I cannot see anything. Maybe at the end. So, Jacek, you know who wrote the paper? Who wrote the first draft of all this?
Sorry?
Who was the author of the draft of the first draft of these papers? Kołos or Wolniewicz, two authors.
I think most of the Kołos was very busy. He commuted between Chicago and Warsaw, and I think most of papers were written by Wolniewicz, the text. But, well, actually, this text was not difficult to write. That was the description of theory. And Wolniewicz was more familiar because it was his theory, with the theory. And as to my knowledge, Klemens Rutan was very much interested in the subjects, and there are acknowledgments to Rutan in all papers, and I think he also helped to formulate papers in correct English, or very correct English. And maybe another anecdote about this: father of Wolniewicz died in Sachsenhausen in concentration camp. He was taken to this concentration camp immediately after the Second World War started. Brother of Rutan also died in this camp, and Rutan was a prisoner in this camp. So they were some kind of...
Yes, I know that Rutan wrote his PhD, master thesis in concentration camp. And this master thesis was considered later on as a legal thesis in physics, but he was forced to work on some military projects led by Germans related to shortwave transmission and solid-state physics. So interesting stories. Separate issue. Okay, I wonder whether it was single precision computer. Was it enough to use single precision for such calculations in terms of numerical
I didn't mention one very important thing.
Yeah?
The main difference between results which were obtained in the first two papers by Kołos and Wolniewicz I mentioned, and the last one was precision. The first two were calculated in, I think, in double precision, and then the next one in quadruple precision, and that was...
Yeah. Let's thank again Jacek, and we go to next speaker, Professor Piotr Wcisło,